All right, let's draw some Lewis structures. So what we see is we have two nonmetals, so we know we're going to draw them covalently. So the first thing we need to do is add up the valence electrons. So carbon has 4 valence electrons, and each oxygen has 6 valence electrons. There's 2 of them, so we're going to multiply by 2. So we have a total of 16 electrons. Now, the next thing we need to do is divide by 2, so we can determine how many electron pairs we will be working with. So we have 8 pairs of electrons that we need to put around these atoms. Now remember, both carbon and oxygen want to have 8 electrons, so they're going to share them in order to get 8 electrons. Carbon always goes in the center, so we'll put carbon. We'll arrange the 2 oxygens around the carbon, and then we draw in our single bonds. So currently we are using 2 pairs. Next step is to put in our electron pairs around all of the atoms except for the central atom. So if we look at this, we've used 1, 2, 3, 4, 5, 6, 7, 8. We've used our 8 pairs. However, we need to go back and double check. Does the central atom have 8 valence electrons? And in this case, it does not. So what we're going to do is we're going to remove a pair from the outside of the oxygen, and we're going to add that pair back. So the oxygen still has that pair, but now it's sharing with the carbon. We still are using only 8 pairs. 1, 2, 3, 4, 5, 6, 7, 8. Is the carbon happy yet, though? Does it have the 8 valence electrons it wants? 2, 4, 6. No, it only has 3 pairs, or a total of 6 electrons. So we're going to do the same thing on the other side. We're going to remove one of the pairs of electrons, and we're going to share them. So at this point, we've used 1, 2, 3, 4, 5, 6, 7, 8 pairs of electrons. This oxygen has these 8 electrons. This oxygen has these 8 electrons that it's sharing, and the carbon is happy in the middle with those 8. Another way you could have drawn this is with a single bond to one of the oxygens and what we call a triple bond, or sharing 3 pairs of electrons. If you notice, the carbon still has 4 pairs or 8 electrons. This oxygen still has 4 pairs or 8 electrons. And we're using 1, 2, 3, 4, 5, 6, 7, 8. We could have also put the triple bond on this side. So if you recall from our notes, these are called resonance structures. What that means is there's more than one possible way to draw this. However, the version that's going to be the most stable is this one. And that's because those electrons are going to be evenly distributed. Up next we have beryllium iodide. And as you'll see, beryllium only wants 2 electrons, and iodine each has 7 electrons. So what we end up seeing is that we've got a total of 16 electrons, and if we divide that by 2, this is 8 pairs. Okay, but what you're probably asking me is, wait, Mrs. Newhoff, beryllium is a metal. However, in this case, because of the electronegativities, it is going to actually want to share some of those electrons. So what we find is that beryllium is actually going to only want to make 2 pairs. It only wants to have a total of 4 electrons. So we always put the lowest electronegativity in the middle. We add everything else around it. We draw on our single bonds. So at this point, beryllium has the 2 pairs, so it's happy. It's done. So we're going to fill in the rest of our pairs. Now I need to double check. Are all 8 pairs used? 1, 2, 3, 4, 5, 6, 7, 8. Yes. Does iodine have all 8 that at once? Yes. And the beryllium is happy with just these 2 pairs. Okay, let's move on to the next one. Here we see magnesium chloride. Well, magnesium, it's definitely a metal. And in this case, the metal is going to want to transfer its electrons. So you're like, but wait, the beryllium, we didn't do that. Beryllium is an exception. There's always an exception to the rule. So for magnesium and chlorine, they're going to follow the ionic compound rules that we've already talked about. So chlorine has 7 valence, magnesium has 2. So because this magnesium can only donate 1 electron to this chlorine, because it can only accept 1, there needs to be a second chlorine to accept the other electron. So what we end up seeing is that we have magnesium, and because it's an ion, I'm going to put it in brackets, with a +2 charge. Each of the chlorines will have their 8 valence electrons with brackets and a -1 charge. Now I'm going to put the other chlorine over here because if you remember, like charges repel, and so those 2 chlorines don't really want to be next to each other. Here we see O2. This is oxygen gas, which you're breathing in right now. So what I know is that each oxygen has 6 valence electrons. There's 2 of them. So I have a total of 12 electrons. I'm going to divide by 2. So I have 6 pairs to work with. So they're going to have to share their electrons in order to only use 6 pairs, but make sure they both have 8 electrons. So there is no central atom since there's only 2 of them. So if I draw in my single bond and I try to use my 6 pairs, so that's 1 pair, 2, 3, 4, 5, 6. I see that I don't have enough to put another pair over here. So what I'm going to do is I'm going to remove a pair and I'm going to share. So if I take a look at this, 1, 2, 3, 4, 5, 6, I've used my 6 pairs. This oxygen has 8 electrons and this oxygen has 8 electrons. Up next, NO. Let's see how this is going to work. 5 valence electrons from the nitrogen, 6 valence electrons from the oxygen. I end up with 11 valence electrons. If I try to divide by 2, is this going to work? No, it's not. I can't have parts of pairs. So what we find is this is not possible. No, not possible. So let's see what Grumpy Cat thinks about that. He probably likes it. Okay, moving on. So here we have 5 valence electrons for the nitrogen, 6 from each oxygen. There's 3 of them. And then remember, if I see a negative, if I see an ion, that means it has lost or gained electrons. And that negative tells me that it gained 1 electron, so I have to add that to my count. So we have a total of 24 electrons, which means we've got 12 pairs. Okay, so I'm going to put my nitrogen in the middle because it's going to have the lowest electronegativity. It's furthest from fluorine. I'm going to add in my 3 oxygens, put in my single bonds, put in my pairs. So right now I've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've used all 12 pairs, however, nitrogen is not satisfied. So what I need to do is remove a pair from one of the oxygens and share it with nitrogen. Now don't forget, because this is an ion, we have to put it in brackets and put the charge. Now if you think about this, there should be more than one way to make this double bond. The double bond could have gone here, or it could have gone here. So this one can show what we called resonance. So there's more than one way to draw this. Up next, nitrogen, so 5 again, plus 7 from each of the iodines. So we have a total of 13 pairs. So you'll notice on the last one we only had 12 pairs and I had a double bond. In this case I've got 13 pairs, so that means I've got that extra pair I needed. So I'm going to put my iodines. Woo! I'm going to add in my pairs. So right now I have used 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here's where my 13th can go. I don't have any ions and I don't have any charges, so I don't need to do any brackets. I'm done. Okay, O3. O3 is actually ozone. So 6 times 3 tells me I've got 18 electrons. I'm going to divide by 2. So I must use 9 pairs. So I have 3 oxygens, so I'm just going to have 1 oxygen and 1 on either side of it. I'm going to put in my single bonds, add in my pairs to the surrounding atoms, and currently I have used 1, 2, 3, 4, 5, 6, 7, 8. So now I put any remaining pairs around the central atom, so there's 9. However, if I take a look at this, is this middle oxygen happy? It's not. So I take a pair, I remove it, and I double bond it. So right now this is happy. If you think about it, I could have done that on the other side. So again, this is another structure that can show resonance. Last up on your homework, we have 5 valence electrons for the phosphorus, plus 6 valence electrons for the sulfur. There's 3 of them. And then remember, I've got my charge here and it's negative, so that means I've added another electron. So I have a total of 24. I'm going to divide by 2. And if you see, I only have 12 pairs again. Now, if I only have 12 pairs, and my phosphorus is in the middle, and I do my single bonds, you should recognize that this looks very similar to this one that only had 12 pairs, 3 atoms around it. And so what it's going to end up looking like is very similar. So if I put in all singles, there's my 12, but phosphorus is not happy. So I'm going to remove 1 pair and share it. So that should look very similar to the last one. It has a charge, so I put it in brackets, and the number, the oxidation number. So what we're going to see is this double bond could have gone here, and it could have also gone here. So once again, we have another structure that can show resonance.